Hello and welcome to the Distributed Systems class. In the lecture today we will cover Byzantine fault tolerance. So we introduced Byzantine or arbitrary failures for processes in one of the first lectures when we discussed various basic abstractions. So to remind you, when we are talking about Byzantine failures, we have in mind failures of processes or faulty behaviors by processes. So a process that is experiencing Byzantine failure is allowed to arbitrarily deviate from its prescribed protocol. So basically it can behave in a faulty fashion in any way it wants. So examples of such faulty behaviors include, for example, situations when a faulty process sends messages it's not supposed to send, or possibly a converse of that it actually not sending messages that it's supposed to send. A faulty process may also form a group and collude to attack the system. So if you look at this diagram showing the hierarchy of different failure models, you can see that Byzantine failures are the most permissive ones in terms of the allowed faulty behaviors. So the crash failures is the most restricted one, then we have omission, crash recovery, and finally Byzantine failures. So also Byzantine faulty behaviors subsume all other types of faulty behavior. So in a Byzantine failure model, a process is allowed to do anything of these three here. It is allowed to crash, experience an omission fault when it omits to send or receive a message. It can crash and recover, and it can also do many more things that can potentially harm the execution of an algorithm. So you might be wondering if there is any practical motivation for considering Byzantine failure model, which is very severe and very permissive in terms of the types of failure behaviors that are allowed. So here are two examples, so kind of the two families of scenarios that can lead to Byzantine failures to actually occur in practice. So the first type of scenarios involve malicious intent of some sort. So here attackers may exploit vulnerabilities in our system in order to gain control of some of the processes and then direct them to deviate from their behavior for the sake of achieving a goal that was conceived by the attacker. So this may include things like causing denial of service, or perhaps committing a financial fraud. So in addition to that, there are also behaviors that actually don't have any malicious intent involved. And those may simply stem from, for example, bugs in the implementation or programming language or compiler. So the family of algorithms that are able to withstand Byzantine failures of processes are called Byzantine fault-tolerant algorithms and are often abbreviated as BFT algorithms. So these algorithms are normally able to operate correctly even in the face of up to a threshold F of the processes in the system suffering Byzantine failures. Examples of such algorithms include Byzantine or BFT consensus, a Byzantine reliable broadcast that we will consider in this lecture, and so forth. So one important thing, or a caveat if you want, to keep in mind is that BFT is expensive. So, and the costs manifest themselves in terms of both failure resilience and performance. So in terms of failure resilience, the BFT algorithms normally only able to tolerate up to the third of the processes behaving in a Byzantine way. And You may remember from our discussion of various crash fault tolerant or CFT algorithms that the thresholds there are typically much higher. So for example, we are able to tolerate up to a minority of failures. So they also typically involve higher communication complexity and exhibit higher latency, again compared to the CFT algorithms solving the same problems. They also normally require computationally expensive cryptographic primitives, such as, for example, message authentication codes, which in turn rely on symmetric encryption. And all these cryptographic primitives are typically computationally expensive. So, for that reason, when designing your system, you have to always consider if the costs of tolerating Byzantine failures are actually justified compared to the potential harm that can be caused by Byzantine behavior. So one example where these costs are actually considered to be justified are mission-critical systems. In this type of system, it might be impossible or very difficult to recover from Byzantine failures if they occur, however rare they are. So examples include financial infrastructure or blockchains and digital currency that recently became very popular, airplane software, and perhaps the software controlling nuclear reactor, and so forth.